Awesome.
All right, everyone, welcome back from the break. Welcome to session E, our final session. This is for hot topics, short paper. So this presentation is only going to be 20 minutes total with Q&A at the end. I'm Ryan Grant. I'm one of the program chairs for this year's Hot Interconnects. You met my other program co-chair, Mincy, in the previous session. I hope you've had a really good Hot Interconnects. This is going to be the last session before we hand it over to our chairs for the closing today. And don't forget that tomorrow we have tutorials all day long that are free to attend as well, courtesy of all of our sponsors. So I'd really like to thank them for that as well. So we just had Jim Handy join us. He's going to be available for taking your questions afterwards. And since Jim introduces himself in the video, I'm going to let him take it away from here. Please enjoy the following presentation.
Hi, I'm Jim Handy of Objective Analysis, a market research, strategy, and analysis firm. You might know me as the author of the Memory Guy blog. Another analyst, Tom Coughlin, and I are here on behalf of OpenCAPI to tell you about the Open Memory Interface, or OMI. Before we get started, I want to make perfectly clear what we were talking about when we say near memory. Many of you have already seen this representation of the memory storage hierarchy. It shows roughly where each memory type fits in, based on its cost and performance, as measured in price per gigabyte and bandwidth. Each of these orbs has its own latency. This shows typical numbers for these. The DRAM that is attached directly to the processor is named near memory. There is currently a lot of interest in adding even more DRAM and 3D cross-point Optane memory and other technologies in memory pools via any of a number of interfaces: SMP, OpenCAPI, Inception, CXL, C6, Gen Z, and even PCIe and Ethernet. These we will call far memory. The focus of this presentation is on near memory, specifically DDR, HBM or high bandwidth memory, and OMI, the Open Memory Interface. With that in mind, I will discuss the need for near memory bandwidth and for larger near memories. I'll follow with some real-world examples of the three current near memory interface types: DDR, HBM, and OMI. After an explanation of how an OMI DDIMM works, I will show how it can support the simultaneous use of a variety of near memory types. So let's jump in. Carl Rupp compiled statistics for the entire history of microprocessor chips from 1973 through today. You can download it from the web, as I did, using the URL at the bottom of this slide. I drew trends for the three data series in this database: transistor count, clock speed, and core count. While transistor count has increased at a steady rate, clock speeds leveled off in the early 2000s. To counter this, designers started multiplying the number of cores to allow performance to continue to increase. This has driven a need for improved memory bandwidth. The standard approach to bandwidth improvements has been to focus on accelerating the speed of the DRAM interface, both through refinements of the protocol from DDR through DDR5 and the bus clock speed. The drawback to this is that capacitive loads limit the frequency of the bus signals. The number of DIMMs that a channel can support keeps shrinking. The common approach to this is to add memory channels, but this comes with its own set of issues. When you add memory channels to a processor, it adds die cost and burns a lot of power. Consider that an LRDIMM channel requires some 152 processor pins. 6 channels almost gets you to 1,000 pins, consuming a lot of the most expensive silicon real estate in the system. Meanwhile, each of these pins presents a capacitive load that burns power when being driven at high frequencies. This has been a concern for some time and has been addressed to some degree with changes to DIMM architecture. DIMMs originally consisted of nothing more than a handful of DRAM chips on a PC board. While PCs still use these, servers migrated to the RDIMM, which isolated the address and control pins to address capacitance issues on these pins at a slight cost in latency. Eventually, the capacitance of the data bus also became troublesome, so another buffer was added to these pins with an additional latency hit. The latency hits, though, were offset by the higher clock speeds allowed with lower capacitance.
But it's not just about bandwidth.
SAP requires considerable amounts of memory as well as high processor performance. This data, provided by SAP, compares the performance of about 90 systems on their standard applications benchmark. Here we use a system's core count times its clock speed as a proxy for performance along the x-axis. The vertical axis gives the benchmark results. You can see that the data points roughly follow a trend with one outlier at the top. What's different about this outlier that allows less powerful processor with roughly a third as many cores as the ones to its right to beat all the others? Incidentally, the outlier is a Power 9 based system with 160 cores, and the two at the far right are systems based on Xeon Platinum 8280L with 448 cores, one from Google and the other from HPE. This is a similar chart from the same data set, but the x-axis now shows memory size, so the chart plots benchmark performance as a function of memory size. From this, plus the preceding chart, we can understand that a less powerful processor with a large memory can outperform a significantly more powerful processor with a smaller memory. OMI not only can support larger memories than DDR, but it can also help by improving bandwidth. Plotting SAP performance versus memory size in this figure, we see that the Power 9 achieves its high performance by using a large memory. Interestingly, the performance is higher than the much larger memory system on the right, based on the high core count processor. IBM tells us that its Power 10, with its 16 OMI channels, provides a socket performance gain ranging from 2.2 to 3.2 times that of a Power 9 with 8 DDR ports. This indicates that SAP performance would be even higher with the OMI memory interconnect for Power 10.
Let's talk about the three near memory interfaces that are available today: DDR, HBM, and OMI.
DDR4 is the mainstream memory, and it makes it inexpensive. HBM costs significantly more, but its 1000-bit bus boosts bandwidth enormously. OMI, Open Memory Interface, is new. It's based on standard DDR DRAM chips, and it provides very large memories at speeds rivaling HBM.
Let's see how some processors support some of these interfaces.
This is a photo of the I/O die, or IOD, for AMD's EPYC Rome processor, which packages 4 or 8 CCDs, core complex dice, with a single IOD. The I/O die supports 8 DDR4 3200 channels for an aggregate bandwidth of 204 gigabytes per second, or 25.6 gigabytes per second per channel. DDR is the most mature of the technologies for near memory interconnects and has been the basis for all DRAM for the past 2 decades. The annotation on the photo shows how much die area is consumed by the DDR I/O on the left and right of sides of the chip. Each of these 8 channels uses about 7.8 square millimeters out of the chip's total area of 416 square millimeters. AMD's EPYC processor packages one of those I/O die chips with 4 or 8 core complex die tiles to attain 204 gigabytes per second of bandwidth, or 25.6 gigabytes per second per DDR channel. Each channel, as I mentioned before, consumes 7.8 square millimeters of the I/O die to yield 3.3 gigabytes per second for every square millimeter of die area. We will focus on these bottom 2 bullets when comparing the EPYC to the next 2 examples. Moving to the high bandwidth memory interface, we have here the NVIDIA Ampere processor, which supports 5 active HBM channels. 6 are called out in this figure, but only 5 are actually used. Each HBM interface has a read bandwidth of 200 gigabytes per second and a similar write bandwidth, since HBM has separate read and write buses.
As the annotations in the figure illustrate, 11.4 square millimeters of the die is consumed by each HBM interface, giving a read bandwidth of 17.5 gigabytes per second per square millimeter, and a write bandwidth of the same magnitude, for a combined bandwidth of 35 gigabytes per second per square millimeter. Note that there are actually 6 HBM2E interfaces on this chip, but NVIDIA only supports 5 of them, so we determined that it was fair to disregard the area wasted on the unused port. HBM is a newer technology than DDR, and has been shipping in volume only since 2015 from SK Hynix, since 2016 by Samsung, and since 2021 by Micron. If we tally up the Ampere the same way as we did EPYC, we see that the chip has 5 active HBM channels that combine to support 2 terabytes per second of read plus write memory bandwidth, or 400 gigabytes per second for each channel. Each channel consumes 11.4 square millimeters of die area to yield 35 gigabytes per second per square millimeter, or about 10 times that of EPYC. It seems like this is a much better choice than DDR. But there's an issue that limits the size of HBM memory. The size of the HBM stack and its required proximity to the processor chip limits the number of HBMs that can be attached to the processor. This photo dramatizes that point. It shows an Ampere chip surrounded by its supporting HBM stacks on a GPU card. Each of the silver rectangles above and below the processor is an HBM stack. The silver color is the back of the stack's top DRAM die, illustrating that it would be impossible to use a smaller package. Although it may be possible to add a few more HBMs at the left and right sides of the Ampere die, this would reduce the amount of space available for the chip's other I/O. HBM supports faster memory, but it doesn't support as large of a memory as DDR. There's another near memory interface option in current production that is neither DDR nor HBM. IBM took a very different approach with its Power 10 processors by choosing to use the Open Memory Interface, or OMI, to reduce the processor area consumed by I/Os while still achieving a high data bandwidth. The OMI memory channel leverages industry standard 32 gigabit per second PHY signaling, but unlike PCIe, the protocol has been optimized for ultra-low latency memory transactions. The 16 OMI channels called out in this photo each consume only 2.2 square millimeters of die area while supporting 64 gigabytes per second of bandwidth. With 16 of these channels, the chip has a terabyte per second of available bandwidth to the memory. Since the channels are only 2.2 square millimeters, OMI provides the processor with 29.6 gigabytes per second for each square millimeter of die area, which is nearly that of Ampere's HBM. This table simply compares those last two figures for each of the interfaces. Clearly, OMI provides about the same bandwidth per square millimeter of die area as does HBM, both of which are about an order of magnitude greater than that of DDR4. But where HBM supports only smaller near-memory sizes, OMI goes in the opposite direction by allowing processors to attach larger memory arrays than can be done with DDR. This is because the processor doesn't need to drive a lot of long capacitive signal lines to multiple banks of memory. This is a slide that we saw earlier that showed how buffers were used to isolate the DRAM's capacitance from the processor. Since there are already buffers on both sets of signals, address control, and the data bus, why not combine them into one chip that has some smarts? This is how the OMI DDIMM works. With OMI, the processor communicates with the memory through a separate transceiver chip that sits on the DDIMM. Microchip, who manufactures the chip, calls it a smart memory controller. The processor communicates with this chip through a differential serial channel that moves data serially at a very high bandwidth. OMI DDIMMs are a mature technology currently produced by Samsung, SMART, and Micron. The smart memory controller is said to add only 4 nanoseconds of latency to the DRAM's access time over a standard registered DIMM. IBM considers this latency increase to be a viable trade-off when compared to OMI's much higher bandwidth than that of DDR4 and the significantly larger DRAM capacities that this approach supports. DDR supports upgrades and multiple system configurations, but it also has limitations since the JEDEC DDR DIMM format was designed to fit within a 1U chassis. JEDEC's OMI DDIMM mechanical specification defines not only a height to fit into a 1U chassis as shown in this figure, but it also defines larger card areas with taller form factors to be used in 2U and 4U chassis. The DDR DIMM's 1U format limits its capacity by the number of DRAM chips that can be fit onto the DIMM. Since larger DDIMM formats can hold larger numbers of chips, they can support higher density modules than can be built within the DDR DIMM standard. The DDIMM uses the same proven differential signaling that is behind PCIe and Ethernet to offer HBM-like bandwidth while using only a quarter as many pins as DDR. Since the DRAM signals are now produced on the DDIMM by the controller, they can be much shorter than they can be on the motherboard to consume less power. Since the controller replaces the buffers on the LRDIMM, it adds less than 4 nanoseconds to the DIMM's latency. The controller itself is not a large chip, so it is not expected to add all that much to the cost of the DDIMM. Future versions will not only be able to support enhanced functionality, but will also allow a processor to communicate through OMI with a variety of memory types. Let's have a look at that. Here we have a Power 10 processor connected to 8 OMI DDIMMs, one for each channel on that side of the processor. What will we attach to it? Well, DDR4 is today's obvious choice, but there's no reason why we couldn't add DDR5 later on once DDR5 prices drop below those of DDR4. Through the OMI channel, these will look the same. In fact, you could make a DDIMM with LPDDR and have all three running in the system at the same time, or you can make the system run on a whole lot of LPDDR. But there are other possibilities too. Just as you can run several different DRAM types in the same system, you can add another memory type, say 3D XPoint, to the system. But it doesn't stop there. A single system could have a different memory type on each and every OMI channel without the processor needing to worry about the differences between any of them.
So where does this lead us?
First and foremost, OMI gives us near HBM bandwidth at larger capacities than DDR. That is illustrated in this chart, where bandwidth appears along the bottom axis and capacity shows on the vertical axis. Note how the OMI yellow box provides almost as much bandwidth on the horizontal axis as the pink HBM box, and more capacity on the vertical axis than the two blue DDR boxes. So to recap, higher core counts require higher near memory bandwidth, and HBM offers that at the cost of memory size. But modern software requires ever-increasing near memory sizes, and although DDR can do that, it's significantly slower than HBM. Systems need near memories that provide both. OMI does this while consuming less processor die area than DDR and HBM. And, as an added bonus, OMI can be used for future systems with a mix of memory types.
And with that, I will take questions.
Okay, great. Thanks, Jim, for that presentation. That was really interesting.
Sure. My pleasure.
I do not have, it looks like people are typing questions in the Slack channel, but I'll start off with a question too. Can you discuss, some performance, depending on the workload, is not just related to the speed of processing and the bandwidth of the memory. Some of it is related to the latency as well. Could you just give us an idea of how important latency is in this whole picture for memory as well?
Well, I'm not going to deny that latency is extremely important for all of this. The problem with DRAM is that no matter which interface you use, the latency is pretty close to the same. That if for HBM, for reasons that I don't fully understand, latency is a little bit higher than it is for a DDR chip, just as a chip by itself. However, DDR chips, no matter what the DDR level, no matter what the clock speed, they all have about the same latency as each other. It just ends up being different numbers of clock cycles. This, any buffering that you do on the module is going to cause a latency penalty, but I don't think that it's realistic, with the exception of HBM-based systems, to direct attach large memory arrays onto the processor chip.
Okay, great. We have a couple other questions. Hopefully we can get to them just quickly before close. Are you aware of any other systems besides Power 10 that are using OMI?
IBM did do some internal work with OMI on a Power 9, but as far as I understand, that's not a released product. So this is a new thing for Power 10.
Okay, great. And what's the largest total DRAM size that OMI supports?
Ooh, I don't remember that off the top of my head. I'm sorry.
Okay. Yeah, it obviously supports a lot of individual DIMM modules, so it should be pretty high.
And too, it's a question of how many of those little ports you want to pepper around your chip. The Power 10 has 16 of them, but I could very easily picture people who needed to have an awful lot of memory putting on more than 16.
Yeah, it didn't look like the silicon area required for it was very large.
I think that's a big point there.
Yeah. Okay, great. So there's a little bit of discussion in the Slack channel. I'll post up a link there, Jim, and hopefully you can follow up with folks who are interested in your technology there.
Okay, yeah. I'd certainly love to help out and to communicate with these people.
Okay, great. I'll send you a link to that.
Okay, good. Thank you.
Thank you.